This week we are going to discuss the discrete event-based model, previously, system dynamics model was based upon the continuous time model, continuous time flow. However, this time the time flows or time occurs, the time advance occurs discretely. So that's being named as discrete event model. And there can be multiple perspectives in seeing this or modeling these types of the scenarios. And what we are going to discuss today is process-oriented view. Okay, before we go further, let's discuss simulation time flow. So simulation is based upon the real world imitation. So let's imitate the real world based upon a certain scenario. Let's say I perceive the time as a sequence of events. So what does it mean? Because that I cannot remember what I did at the 600 a.m. or the 700 a.m. exactly. However, I do have some recollections of a time fragments that I did something very important. For example, do you remember what you did at 9:37 a.m., 9:38 a.m., 9:39, 9:40? What were you doing? What were your state? How can I describe your state at that specific time? Maybe very difficult to describe such kind of continuous time flow. However, do you remember when you had your first coffee today? For example, let's say that. I do remember. I just went to my office and the first thing that I did was like opening the window and I made my coffee, right? So that was around 9:30 a.m., right? So I attended class at 10, so there were 23 minutes that I enjoyed my coffee, right? So what I want to say to you is that we perceive time as a discrete event, as a person being, right? I cannot remember what I did at 9:39 a.m. or 9:40, 9:45. What I do remember is the point of time that I did something that could be remembered, right? Which I would refer that as an event. Okay? Scanning all perceivable events occur to me is feasible. So that for me, time doesn't flow like this continuous change of state like this. Okay, I drank coffee that much per second. This is the continuous time flow. I cannot remember my state change for each of those time slices that I noted here, which is a very frequent time sampling to imitate the continuous time flow. However, discrete value time that I remember is that, okay, I did a certain activity so that I change it. I did certain activity here, so I changed my state. State transition event. State transition event could be remembered for each of these time flow. Of course, I did not say that this event occur regularly. Then it's a discrete time like digital system. However, I'm not saying that the time is continuous dimension like this. It's continuous. At any given moment, event can occur. However, what I remember, what I model is the continuous time of that fragment that event occurred. That is the discrete event model. So that I remember the event. Then, what do you remember? Why do you remember these events? Because these events change your memory, action, thinking, intention. And what I'm saying, what I want to tell you is that these are all coming from or summarized as what? State of your system, of your inner body system or inner thinking system, state. Okay? If you are a system, the event changes your of course, state. Okay? And let's say that this was a single person's personal event of throughout the day. However, let's say that we are modeling a society. We have multiple persons, people, right? More than one person. In that case, state occurs independently or jointly, and then eventually this discrete event, right? Because we are not going to continuously sample each of these small advances of time fragments, so that what is important in the system dynamics model, dt ds or dt dx, dt dy. And this delta time is a very small advancement of time. That was very important in modeling the system dynamics model. However, we are not going to discuss that any further in the discrete event time model. Okay? Later, we are going to report that to the transition function, state transition, and state transition will occur irregularly, and for society there will be so many events, and events will occur many occasions, and we have to find out which events will affect which states and how. Now we turn our discussions to the finite state machine. So now we know that state changes by the events. And how does that state changes? How can we specify such changes? Previously, system dynamics model was differential equations, basically dx over dt. Having said that, we need to further formally represent the state changes in those discrete event models. And one of them is the finite state machine. There are two outstanding finite state machine representation methods. One is the Moore machine and the other is the Mealy machine. And we are going to discuss Moore machine alone in this scope of the lecture. So we define the finite state machine here. What is finite state machine? It's an abstract machine. It's an abstract description of a system ladder that can be in one of a finite number of states, right? And the machine can be reside or can be specified to be in only one of the states at a time. Okay, so there is a certain state in any given time, not multiple, right? And the state of the machine changes when initiated by a triggering event or condition. And now we are going to call such kind of state change as transition, so that this is a common terminology in terms of the modeling and simulation. Okay, we are given a state, and then eventually or fundamentally we are also modeling its transition, state transition, right? So particularly when we use a finite state machine to model a state changes, we can utilize a certain diagram like this, okay? And these model state changes require, we should be able to enumerate possible states, okay? Potential states. And we need to specify how it will change, how the transition will occur by the triggering events. That those two need to be specified. And these notations specify that. So let's say this. Let's look into this. Notation of finite state machine. First, we need to define the state. Okay? So this is a formal representation or graphical notations of the state. And we remember causal loop diagram or system dynamics model. And they have their own graphical representation model, right? And same thing. This is an abstract representation of this finite state machine. So first, the circle here will be created for each of those states. Okay? State, right? However, there is the state is being annotated by open state or closed state, right? And then we need to specify its transition. transition from the opened to the closed. So that transition will occur from the open to the closed. Okay? So that this transition will be called or will be named as closed door, and that is being the transition condition. Okay. After that, if this state machine does something or represent outside a certain do some activity to the outside world, then we can define that entity's action, then modeled system's action in that state with this statement. So here closed state will say closed door. Okay, and then transition condition, if that is being met, open door, then state will be changed to the opened. And outside world, the state will claim that it's open door, right? So that is being the entity action being stated, right? So briefly, I went through the notations of the finite state machine. So where this finite state machine is being often used, it's mostly often used in the electrical engineering community society. Okay, so this is really a digital system designing method, and that's where this Moore machine, Murray machine has been developed. And also computer programming, because that this is very logical statement of the changes of the system. So computer programming also has been benefited from these types of the research. So let's discuss one example of the finite state machine which follows the Moore machine specifications. Okay, so Moore machine is a type of state machine that outputs values all the entity actions by following his current state. Okay, so the previous notations were really matching the Moore machine because the state will output its entity action, the output values, right? So here in our context, input are the triggering event, state transition event, and output are the actions toward the real world output. Okay. So let's look into this. So this is one particular notation of the finite state machine, right? Do we have state? Yes, state 0, state let's say 1, state 1, 1, state 0, 0, state 0, 1, state 1, 0, state I, state initial. Okay? Do we have entity actions? Yes. 0, 0, 0, what to output, how to output, right? And then do we have a triggering event? Yes. 0, 0, 0, 0, 1, 0, and so forth. So we have all the things necessary to define a certain finite state machine. Okay, so we have state, we have transition link, we have event. That's all fine. And now, this state machine is modeling this question mark system. And its input is being specified like this. Then let's look into this and try to identify what to be the output. So where do we start? Well, where do we start? We start from the state initial. Okay? State initial. That is being output like 0 at the moment. That is producing 0 at the moment. And then our input, transition triggering event, is inputting 0. So that transition will occur. Then it's going to move to the S0. So I will put Si to S0, right? And it is being output like 0, 0, right? Because state being changed. And then we have 1, and that will transition our state from S0 to S01. And then output will be 1, 1, 1. Right. And then we are going to get 0. You are going to get 0, and then we are going to get 0 means that we are going to reach S10, and either output 1, right? And then we are going to get 1, and then transition to where? Transition to S01, and the output will be 1, right? Right. And again 1. Then either make S11, and then output will be 0, okay? And then again the input is going to be 0, then it's going to go to S10, 0, right? S11 from S11 to S10, and either output 1, right? And that's the end of the input, and that's the end of the output of this finite state machine. Okay. And then the result will be, so this if we disregard this initial output, then the output will be this 0, 1, 1, 1, 0, 1. That matches up, the transitions matches up. Okay? So this is how you logically simulate the finite state machine, and that is basically what is happening inside of your digital system.